Stripping down science. The Naked Scientists.
Hello, it's Sunday, April the 3rd. Welcome to The Naked Scientists with me, Chris Smith.
And me, Dave Ansell.
This week we're celebrating the anniversary of the first mobile phone call. It was made on this day in 1973 in New York. Now, almost 40 years later, the number of mobile phones on Earth has grown to over 5 billion, nearly as many as there are people. And even Everest now has coverage thanks to a mast which has been installed near to the base camp, which is ironic given that you can make a call from Everest, but I can't even make a call from my village just outside Cambridge. But are mobile phones actually safe? Well, we'll be talking with the researcher behind one of the world's largest scientific studies, which has been set up to find out.
We'll also hear how scientists are developing new ways to keep the conversation flowing by correcting the errors in mobile phone signals caused by poor reception. It's a trick that can also save scratch CDs from the dustbin.
We've drilled some holes at the beginning of the first track of this CD. The CD uses an error correction mechanism, which should be able to, well, hopefully play the sound, despite the fact that we've drilled holes in it. So it should be able to overcome the channel disturbance that we've introduced.
You can hear how that CD sounded when we played it later in the show. Chris.
Thank you, Dave. Plus, we've also got news of how a chemical can combat a fear of heights and why the worm opinion polls that are shown during live TV political debate could be seriously biasing voters. Meanwhile, if you have any comments or questions for us, then tweet them to @NakedScientists. You can post them on our wall at nakedscientist.com/Facebook or drop us an email, of course, to chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with Chris Smith and with Dave Ansell. First up, let's take a look at some of this week's biggest scientific breakthroughs. Dave, what have you got for us?
Well, the Pioneer anomaly appears to be rather less anomalous than people previously thought. The Pioneer anomaly sounds like some kind of thriller novel, but it's actually a slight acceleration on the Pioneer probes. These are space probes launched in the 70s and are some of the most distant man-made objects that we've made. As they headed away from the solar system, their path was carefully tracked and a strange anomaly was discovered. They were decelerating slightly faster than they should be according to Einsteinian gravity. The effect was tiny, about 1 part in 10 to the minus 10 metres per second squared, but it was measurable and it got lots of theoreticians very interested. This is because studies of galaxies indicate that gravity may be stronger at larger distances, and this would tend to agree with it. So theorists have been creating lots of new theories of gravity to fit this data. In 2008, a third of the anomaly was explained by Federico Francisco and colleagues. The spacecraft generates power by heat produced by radioactive decay. This heat is lost by thermal radiation, which is a form of light. Light carries momentum, so it can apply a force to the spacecraft. It's like a very, very weak rocket. They hadn't managed to explain the whole anomaly even when they'd taken into account all the heat sources. Now they think they have. A source of heat, the main electronics compartment, is immediately behind the parabolic dish the spacecraft uses to communicate with Earth. So thermal radiation from this electronics will reflect off the dish, giving the spacecraft a slight extra deceleration, explaining very, very neatly the anomaly. So unfortunately for the theorists and their chance of a Nobel Prize, Einstein's equations seem to still hold.
All I can say about that is oops, because lots of people have put lots and lots of time into developing things that fit dodgy data, basically. It's nice that they've now solved it, but also, what about the people who've come up with all these other explanations? Did they lead to anything useful, or is this now completely in the dustbin?
I'm sure they'll keep looking at their experiments and trying to find other data which doesn't quite work with Einstein. It's all a good intellectual exercise, if nothing else.
So the moral of this story is don't disagree with Einstein, I guess. Have you got a head for heights, Dave?
It's not the best.
Me neither. Maybe this could help you. There's a study which has been published in the journal PNAS this week. It's by Dominique de Courvin and his colleagues. And what they have done, they're based over in Europe, what they have done is to recruit 40 people with diagnosed acrophobia, fear of heights, and they've divided them into 2 groups. So both groups, an intervention group and this control group, were given what's called graded exposure therapy. So when someone's scared of something, one way that you can help to desensitise them is you expose them in a graded way to the thing that they find worrying or scary. You let them get used to being frightened, And then when they say they're calming down a bit, you expose them a bit more until eventually they learn to overcome their fear. So they put them into that kind of exercise. In this case, what they did was to put them in a virtual reality headset, which showed them climbing up all these platforms, making it look like that they were teetering on the brink of all these precipices, which would be terrible if you fell off. And of course, it is very realistic, and it makes people think they are literally going to topple off this building. Now, as they did this, they're asking them, OK, how stressed do you feel? And when the people report that they feel better, they make them go even higher, and so on. And so that was the sort of therapy they were doing, and they did that 3 times to both the groups. But the critical difference between the 2 groups of people was one of the groups got given a dose of a chemical called cortisol. And cortisol is one of the body's natural stress hormones. It's produced by your adrenal glands when you get stressed about things, but after you've had the stress. So when people get stressed, they make this cortisol chemical, which goes around in the bloodstream, and we know it influences the way that the brain works and the way that you process certain bits of information. So what they then did was to follow up these people after they'd had their 3 treatments at 3 days and at 28 days after they'd been exposed to these heights. They repeated the exercise and they measured how stressed the people got. And what was really interesting is that the control subjects improved. In other words, they reported 30% less stress after this. But the people who'd had the cortisol had 60% less stress afterwards. So they had got very, very much better than they used to be at dealing with heights. And you then ask, well, why should we see this difference when you give these people this natural body chemical to take? And the answer is that we know that cortisol goes into the brain very well. When it goes into the brain, it impairs recall. It makes it harder to remember things. And this is important because in courtrooms and things where you're putting people in stressful situations and asking them to recall minute details of the proceedings of a case, that can be tricky if you've got a hormone going around which is going to impair recall. But the important thing is that it also reinforces the establishment of new memories that you're just about to make. So by giving the people the cortisol, they made it harder for them to remember that they were scared in the first place, and they made it easier for them to remember that actually it was fine and they survived after all. And the researchers say, look, it's a natural chemical, it's very few side effects, and therefore, given that this strategy worked for heights, it could well generalise to other phobias too.
Why should cortisol have that effect naturally?
One would think that it's some kind of evolutionary behaviour whereby if you have a system where when something makes you stressed, you need to pay attention and learn very well what caused the stress and how you got out of it, if assuming you survive, and therefore it helps you to do that, and it doesn't have you remembering all kinds of spurious things that you don't need to remember at the time that you're facing the stress. I would guess that would be the best interpretation at this time. Well, in last year's general elections, we had the exciting spectacle of a leaders' debate. And to help us get an idea of how well the speakers were doing, we could watch The Worm, which is a real-time computer-generated graph that shows how much a subset of the audience either approve or were disapproving of the comments that the leaders were making. But could this be having an impact on the audience and also on the voter by biasing them? Professor Colin Davis from the Department of Psychology at Royal Holloway, University of London, has been trying to find out.
So the worm is something that has been around for quite a while. Initially it was something that was used particularly by politicians so that they could see for themselves how well their message was playing. And then at some point people in television thought, well, this is interesting for the viewer as well, so we should give them access to this information. They can find out what voters think about different things that the candidates are saying. But the question that we were particularly interested in was what effect the worm might be having on what the viewers at home thought about the debate and what the candidates were saying.
So how did you actually do the study?
Well, we ran what was really conceptually a very simple experiment, although technically it was somewhat difficult. We had 2 quite large groups of subjects come in on the evening of the final election debate last year, on April 29th. And they watched a version of the debate that included the worm, so this squiggly line going up and down. But we played a little trick on our subjects, because although they were watching the genuine live debate, which we were getting from the BBC stream, the worm that they were seeing wasn't the real worm. It was controlled by us. So I was sitting in my office watching debate and pressing some keys to move the worm about and hopefully making it look plausible. And the worm that our subjects saw was based on the one that I was moving about, but which was biased in a particular direction. So for one group, the worm was systematically biased in favour of Gordon Brown, And for the other group, it was biased in favour of Nick Clegg. And then we used some video mixers so that we could superimpose our worms over the live BBC broadcast. And based on people's responses afterwards via questionnaire, we can tell that our deception was successful. So the subjects on the whole believed that this was a real broadcast, the worm was genuine.
But more critically, what was the outcome when you asked the students who won the debate then?
Right, so what our results suggest is that actually the worm is having a huge influence, in fact, much greater than we had even anticipated. So our two groups had completely different ideas about who had won the debate, and their opinions were consistent with what the worm had been telling them. So the group that saw a worm which favoured Gordon Brown thought that he had won the debate, whereas the group that saw the worm which favoured Nick Clegg overwhelmingly thought that he was the winner. And more worryingly, perhaps, we saw a similar, perhaps slightly smaller effect when we asked people about their choice of preferred Prime Minister. So, if people had been voting immediately after this debate, it seems like our manipulation could have had a significant effect on how they voted. But
it's only manipulation if the indication given by the worm is artificially biased or it's not based on a big sample size. Because if it's representative of the population as a whole, then that should be fine, shouldn't it? But how many people then are those worms based on? If we look at what the BBC did, when they generate that worm, how many people are they asking to produce that data that we're seeing? Well, that's particularly concerning. So the BBC's worm was based on only 12 undecided voters for each candidate. And that's pretty typical. The ITV had their own worm, which was based on 20 undecided voters. CNN in the US used the worm for the presidential debates in 2008, and they had 30 voters for their worm. So, very small samples, much smaller than those that you would ordinarily use for political polling, could very easily be affected by a small number of outliers, could very easily be deliberately manipulated. Because I think the point that you've made in your paper is that the whole point of these TV debates is to try to present the leaders in an impartial way without any media spin and filtering. And as soon as you impose a statistically totally implausible group like 12 people on something like that, generating this worm, you completely skew everything, because 12 people is such a tiny sample that... And given that these are people that are probably recruited local to a TV station, if you just hoik out the local population and put them in, you've got a terrible sub-selection problem, haven't you? Yes, you've really got no guarantee that you will have a representative sample. And I think there's also some cause to be concerned about partisan forces attempting to manipulate this. I mean, one thing we know, for instance, is that The Guardian had their own worm, what they called a sentiment tracker, and clearly no one would claim that was a representative sample, but it's interesting to note that the Liberal Democrats were caught trying to manipulate the Guardian worm. So all of their staffers from Liberal Democrat offices were using lots and lots of computers to vote in that. Beyond that, though, yes, as you say, the debate, if it works well, is about giving viewers a chance to form their own opinion in a way that isn't affected by media spin. And the worm is stopping them from doing that. When we see after the debate spin doctors come on, Alistair Campbell say, well, Gordon Brown clearly won the debate, we have the opportunity to think, well, clearly he's biased. But the worm is much more insidious than that, and I think that's a real concern. And just to finish off very briefly, Colin, what would be your proposed solution? Should the media users be reporting where their sample comes from and what scale it is, how big their worm sample is based on, so that people have some chance of making, therefore, a judgment as to whether it can be relied on? Or should we just ban it altogether? Well, my preference would be to say that we shouldn't have a worm at all. If there is going to be a worm, then I think it should be very tightly controlled. And in the same way that there are quite strict rules about the opinion polls that you see in newspapers, there should be rules governing the worm. So it should be very clear how it's been created, what the sample is that were used, and so forth. Fantastic. Thank you. That's Professor Colin Davis from Royal Holloway, and that's the University of London, of course. He's published that work this week in the journal PLOS One. Dave.
Brilliant. Now, a way of powering chillers with just waste heat is being improved. Even in the UK, air conditioning is becoming more and more popular. In parts of the world with a less temperate climate, it's a huge use of energy. Along with other forms of cooling for fridges and server farms, it all adds up to a huge amount of power use. At the same time, a large amount of potential work is being wasted from low-grade heat from industrial purposes, or for that matter, from the sun. One way of taking advantage of this is called an adsorption chiller. These work by having two chambers covered in silica gel, which attracts water molecules onto its surface, a bit like a sponge, so it dries out the air. One of these is open to whatever you want to cool, which is covered with water. The water evaporates from there, cooling that area, and then condenses onto the silica gel. Eventually the gel becomes saturated, at which point you use the other chamber to adsorb the water. Meanwhile, the original chamber is heated to 70 or 80 degrees centigrade, drying it out, and then you recondense the water and recycle it. These can cool down water or air down to about maybe 4 degrees centigrade using a tiny fraction of the electricity of a conventional cooler. But normally they're at least 4 or 5 times larger, so they're very impractical and uneconomic to use widely. Peter McGrail and his team have been working on replacing the critical silica gel. They're constructing materials made up of metals and inorganic molecules, which can be engineered to self-assemble to form very open structures with a huge surface area, which should mean that the material can absorb 3 or 4 times more water than silica gel, weight for weight. Plus, the strength of the bonding between the water molecule and the surface can be very carefully tuned, allowing them to optimise the temperature of the waste heat you're using and how cold you want to cool your cold end, making the process far more efficient. This opens up the possibility of cooling computer server farms with waste heats from a power station, or even have air conditioning powered by the heat from the sun.
So we'll have nice cool homes in the future. Let's hope so. Thank you, Dave. Well, just to finish off this week, interesting discovery which has been published in the journal Nature this week. Gordon Lithgow and his colleagues, they're based at the Buck Institute in America. They've actually discovered that a dye which has been lurking under our noses for a very long time, it's used in pathology laboratories to stain tissue in order to look for what are called beta amyloid deposits. Beta amyloid builds up in the brains of people who have Alzheimer's disease, for example. It's a pathological protein. They wondered, well, if we've got a dye which binds to it to show where it is, could this dye also be given to something so it would go inside the body and bind to the aggregates and make them less harmful, because what these aggregates can do is damage brain cells, and they do lead to Alzheimer's type diseases, for example. So they started using this chemical. It's called thioflavin T, THT, and they didn't use mice or humans, but they did use microscopic worms called C. elegans, which are very well understood genetically and anatomically, so they're very good, cheap, easy, reproducible study subjects. They started giving them this dye at low doses, and they found the worms, just healthy worms, lived 80% longer in some cases, and as Gordon Lithgow says, they looked younger and they moved around a lot more, even when they were older. Now, to find out why this was happening, they then started using some genetically modified forms of these worms, which have been programmed to develop a worm equivalent of an Alzheimer's type condition, where they get a paralysing muscle state. And they found that the levels of paralysis in these worms, when they were given this dye, was 20% of control animals that didn't have any of this dye. When they went hunting for why this is happening, they found that several things are probably going on. One is that the dye seems to turn on genes in the worm, and they now know what some of those genes are, which make cells better able to defend themselves. Specifically, what that means is that they mean that the proteins in the cells that normally tangle up and misfold themselves to make these beta amyloid deposits, those proteins are much more stable because the cell looks after them better. And also, the dye directly binds to the proteins and stabilises them itself. So where could this lead us? Well, what they're saying is that as we now understand the chemistry of these dye molecules quite well, if we go looking for other molecules that have a similar chemical nature or structure, there may even be some which are already in the formulary used to treat other conditions. They may well have the same action, and we could therefore have a way of stabilising the proteins in the human body which give rise to diseases like Alzheimer's disease and preventing those diseases progressing using this sort of technology.
Is it likely to have other effects on lifespan as well as just Alzheimer's? Because it appears with the worms that a really huge part of their ageing seems to be this build-up of proteins.
Well, it's not just the build-up of proteins, it's that in all of us, as we get older, proteins do tangle themselves up the wrong way. And this includes making cataracts in your eyes. The reason that the lens in the eye becomes foggy with age is because the crystallins, the proteins that make the matrix of your lens, eventually tangle up the wrong way, and they, instead of letting light go through smoothly, they scatter it all over the place. So this happens sort of commonly in many tissues of the body. And if you can find chemicals that bind to these proteins and help to lock them into the right shape, they find it much harder to form the wrong shape, and therefore you remain viable and healthy in all your tissues for much longer. Well, that's it for the news this week. If you'd like to follow up on any of the items that we've covered, then the references as well as transcripts of those stories are on our website. That's at nakedscientist.com/news.
Laying the facts bare. The Naked Scientists.
You're listening to The Naked Scientist with Chris Smith and me, Dave Ansell. Coming up, how a huge study should finally answer people's questions about the impact mobile phones have on our health.
But before that, some clouds can be identified easily from the ground, but others with more difficulty. But when weather forecasters and academic researchers need a bit more detail about what's up in the air, then they turn to the Chilbolton Facility for Atmospheric and Radio Research in Hampshire. Now, these guys can put the world's largest fully steerable meteorological radar, known as the Big Dish, to work, as Planet Earth podcast presenter Sue Nelson found out with the facility's head, Charles Wrench.
This dish is 25 metres diameter, and it's fully steerable, which means that we can scan it in both elevation and azimuth to track storms or clouds as required by the researchers who come to use the facility.
How easy is it to actually steer? You say fully steerable, but I can't imagine how you would actually begin to steer something of this magnitude and height.
It is a big structure. It was originally designed for radio astronomy. We don't use it for that purpose right now. We're using it for meteorological research. But with computer control in the control room, we have our radar scientist who is just about to actually start it up for us, and you'll be able to hear the system operating. That's the klaxon to warn anybody outside that the dish is about to start moving. We're now doing an azimuth scan, so it's a fixed angle of elevation, and it's going to rotate through 360 degrees.
That's amazing, because it's very smooth. I mean, we heard a slight sort of frictional screech of a startup.
The brakes letting go. The brakes let go, but now it is actually very quiet. We've recently had the servo system upgraded. Before that, it sounded a lot more impressive, a lot more noisy, but now it's very quiet, very smooth.
It's turned through now this enormous dish in a very short period of time. It will be at 90 degrees.
It does actually rotate at 1 degree per second. So a 360-degree scan will take you 6 minutes.
Well, as it's scanning round now, this enormous dish looking out across the Hampshire countryside, let's just go into, Charles, what sort of technology you're using here. Obviously an enormous antenna like this. There's a squish there.
The antenna is a very large structure. There is a multi-parameter 3 gigahertz radar on the dish, and with that radar we're able to characterise in great detail the structure of storms, precipitation, convective storms. With that radar we have a 0.25 degree beam, and that's a very narrow pencil beam, and it means that we can move it around within the convective storms, and we can look at the structure going on within those storms.
You're bouncing off effectively then
Yeah,
a radio wave, a beam on clouds, the sort of clouds that are above us today.
Yeah, we're transmitting pulses of radio wave energy, wavelength of about 10 centimetres. And what's happening is those pulses of energy are being transmitted out into the sky. They're finding targets, and you're getting a small amount of power reflected back. We're actually diagnosing how that power looks when it returns to us, and so that we can then establish particle sizes, particle types, particle phase, i.e. are they ice, are they liquid, within storms or clouds.
You've also got a smaller dish. I mean, that one is only a metre or two across. So how many other dishes do you have around the site?
That's a 35 gigahertz radar. That's designed specifically for looking at cloud structures. We use higher frequencies for clouds because the particles within clouds are smaller, and therefore you need a shorter wavelength to detect them effectively. In terms of dishes on the site, I think we've probably got 3 of that type.
And what about behind it? Because when I arrived, behind there was a sort of even smaller dish and what looked like a plastic owl.
Right. Yes, indeed, that is a plastic owl. We have a multi-frequency microwave radiometer, and we use that radiometer for measuring water vapour profiles in the atmosphere and the liquid water content of cloud. You mentioned the plastic owl. The owl is doing a very good job protecting the instrument from the attack of birds in the vicinity.
I might try that myself. That was Sue Nelson with Charles Wrench. They're at the Chilbolton Facility for Atmospheric and Radio Research. And you can download the latest Planet Earth podcast, as well as other Planet Earth online resources, from our website, nakedscientist.com/Planet Earth. This is Chris Smith and Dave Ansell.
We're looking at mobile phone technology this week, so for Naked Engineering, Mira and I have been to Cambridge University's engineering department to look at the research they're doing there to improve the quality and reliability of mobile communications. Dr. Albert Guillen explains what's happening when you're having a conversation.
So the first thing that happens is that your speech or speech signal is translated or converted into an electrical signal inside of your mobile phone, which is then digitized and reconverted into a long string of zeros and ones, which are, again, remapped into a different type of signal, which is suitable for transmission from your mobile phone antenna. And this signal then arrives to the nearest base station, which then puts you through the next level in the phone network and eventually connects you to the office.
So say while someone's out on the move, their environment is constantly changing. So how is this signal changing?
When we move, the signal that either we or the base station transmit bounces in buildings, cars, other users, trees, and we have no way of knowing what the signal is going to be. Sometimes these multiple paths or multiple signals or multiple bounces of the signal will add constructively, so we will have a very good reception, and other times these components will add destructively. The mobile phone periodically trains itself to learn what the channel characteristics were. Then, using that information, it can reliably recover the data. Often what happens as well is that information is transmitted in different frequencies, and if one of the frequencies is down for whatever reason, then information can still be restored from the remaining frequencies.
I guess even this isn't going to produce you a perfect signal, and if you've originally compressed the data very, very hard, even a few errors are going to cause complete havoc with the sound. I think this is where your work comes in.
Yes, this is right. What the mobile phone does is adds another building block called error correction, and it does it in such a way that even in presence of errors or even in presence of destructive interference or fading from the channel, we can still recover our data reliably. So, for example, one simple way one could think about this is to repeat the original compressed bit stream, to repeat it twice or three times. This clearly adds redundancy, but it would make transmission more reliable, but the data rate will suffer significantly. Instead, what all communication systems use are error correction codes that are mathematically more sophisticated than this simple repetition code. One prime example of that is what it's used in the CDs, where a code called Reed-Solomon code is employed.
We've now come down to one of the engineering workshops where Dr. Yossi Sayer is busy drilling holes into a CD. Now, Yossi, this does actually relate to what we've been talking about, mobiles. Why are you drilling holes into these CDs?
So I'm trying to illustrate on the CD how error control coding works. We've drilled some holes at the beginning of the first track of the CD. The CD uses an error correction mechanism, which should be able to, well, hopefully play the sound, despite the fact that we've drilled holes in it. So it should be able to overcome the channel disturbance that we've introduced.
They've put this in there so even if you scratch your CD, it's not completely worthless.
That's the idea, right?
Well, we do have our wonderful Naked Scientist theme tune on this particular CD that you've drilled away at. So let's see if this hole, which is about 2 millimetres wide, has made a difference and whether this track is still going to play.
So I'm going to put it in now, press the play button. Hopefully it'll work. Here we are.
Stripping down science. The Naked Scientist.
That hole was pretty much towards the beginning of the track, and as we heard there, it was still playing very smoothly.
Basically, what's happening here is we've added structure to the data. I think the best way to think about it is to think about Sudoku puzzles. the information would have been encoded onto this CD as a full Sudoku puzzles. By drilling holes or scratching the CD, we're erasing some of the information, which is very similar to what's happening in mobile phones, where the wireless channel is doing that for us. And the task of the reader or the receiver in the case of wireless communication would be to fill in those gaps and try to guess at the missing numbers.
And now moving back to you, Albert, then, what about the different types of signals? So 1G, 2G, 3G, GSM, how do these differ really? And how does maybe error correction differ, or the handling of these holes differ with these different types of signals?
So the major change occurred when GSM or 2G was introduced, because GSM was the first all-digital wireless communication system which featured error correction, data compression, while 1G was an analog communication system. And now future generations, including 3G, 4G, 5G, the main aim will be to progressively adapt to the channel characteristics and allow to transmit higher and higher data rates. And in order to help us achieve this goal, future systems will also feature multiple antennas at transmitter or the receiver, which will help us increase reliability and data rate.
That was Dr. Albert Guillen, and before him Dr. Yossi Sayer, both from the engineering department at the University of Cambridge.
Thank you, Dave. It's Chris Smith and Dave Ansell. We're talking about mobile phones, and they're totally taking over the world at the moment. I've got some stats here, which I'm grateful to Anthony Lewis, who pointed us at an infographic, which has got various statistics. In 2014, this informs me, mobile internet usage will overtake desktop internet usage. In other words, more people will be accessing the internet from a phone than using a computer, which is interesting in itself. But this one's really quite staggering. Children are more likely to own a mobile phone now than a book, it says, with 85% of children owning a phone and 73% having books. Isn't that a sign of the times? Dave?
As the demand for mobile communication devices increases, we're demanding progressively faster data transmission rates. One option to improve this is to install multiple antennae into a device so there's lots of streams of data that can be handled in parallel. This comes at a cost in size, or does it? Scientists at Bristol University have come up with a way to share the antennae of nearby devices to get around this problem. To explain how this works is one of the inventors, Professor Mark Beach, is with us. Now, Mark, should we start off really simple? What limits the amount of data which basically two straight aerials can transmit between one and another?
We're very limited by the channel bandwidth that we can provide to mobile communication systems. So that the bandwidth is the main driver, followed by the amount of power that we allocate to the transmitted signal, which we can increase to improve the data communications, but that then causes interference to other users and overall would then reduce the capacity of the system.
So the bandwidth, this is the effect that if you starting off with a pure frequency, the more data you put on that, the more frequencies that uses at once.
Yes, that's right. As we expand the data rate, we get a corresponding increase in the bandwidth of the signal needed to transmit the information between A and B.
I guess there's a limited number of frequencies out there or that I could use, so there's a limit to the number of people who can talk at the same time or surf the internet at the same time.
Yes, that's true. The frequencies around 1 to 2 gigahertz are really the sweet spot for mobile communications, where the signal propagates well with less attenuation, and the physical size of the antennas used allows us to put them into mobile devices.
I guess the whole of this problem, it's a bit like having lots of people talking into a room and one person on one side of the room is attempting to listen to someone on the other side of the room and kind of filter out all the other people talking at the same time, so all these different mobile phones. So one of them is to talk at different pitches, so you might be able to hear someone speak at a high pitch on the other side of the room if everyone else is speaking at a low pitch. But you're using a slightly different approach.
What we've been looking at is the use of multiple antennas to increase the transmission bandwidth of information by exploiting the multipath in the channel that we heard about a few minutes ago. So the multiple antennas excite the multipath, and at the receiving end we can separate out the multipath signals, and we resolve these individual spatial channels that we can push information down in parallel, and we can do this on the same frequency and at the same time.
So I guess that this multipath is whereby if you're standing next to a big reflective building, the mobile phone message can get between your phone and the mast in two ways. You can either go straight there or reflect off the building. And if you've got a very complicated system, there's lots and lots of different reflections. And so you're somehow taking advantage of this.
Yes, we are taking advantage of the multipath signature in the channel. And when we have multiple antennas, we will actually see slightly different signatures. And those signatures can be quite unique, and we can use those spatial paths independently to support communications.
Does this mean that if you've got lots of different aerials in one place, you can actually build a directional aerial? So you can put them together in one way, so you can just listen to the reflection from the building, and you can add the reception from your different aerials together in a different way to listen to the direct signal from the mobile phone mast, so doubling your data rate.
It's along those lines we can actually beamform the information down these spatial paths and extract them at the receiver. And the theory tells us that if we double the number of antennas, we can double the data rate. And if we go up to 4 times the number of antennas, we'll have 4 times the rate, providing there's sufficient multipath richness in the channel. There is eventually a trade-off with the number of antennas and the actual benefits that you will see.
Can you just carry on adding more and more antennae into something the size of a mobile phone with no problems at all?
There lies a problem. Although I mentioned that the frequencies around 2 gigahertz make quite small antennas, there is a limited amount of real estate in a mobile phone where you can actually place these devices because of the other electronics inside the box, in particular the display on smartphones. So we are somewhat limited. Probably between 2 and 4 antennas is probably about the limit that you could actually put in a portable device.
So what are you doing to get around this problem?
Right, what we've been looking at is actually sharing antennas. So perhaps somebody else's mobile phone, which was enabled with multiple antennas, if they were not using it in conversation, we could share those antennas and actually use them to form our communications link, thereby making perhaps the 2 phones slightly simpler in terms of the number of active antennas that they would need.
So you'd be sort of essentially joining the 2 mobile phones together with, instead of a wire, with another wireless link, which is very short range.
That's right. So we would form a virtual MIMO system between the 2 devices and then have a short range, low power link between the actual users.
So I hear you've actually been using this in practice. How has it been working?
We've been looking at this using quite a sophisticated channel sounder that measures the multipath signatures of the channel. So we could see if we actually separated the antennas and say had 2 with one user and 2 antennas with another user, does that actually form a good 4x4 MIMO system?
So were you getting a speed up on average?
On average, yes, we do. One of the things about MIMO communications is that you require this independent fading, so we can get these separate spatial channels. So by moving the antennas further apart, that normally gives you much better characteristics. So we found from real measurements done in the city of Bristol that for at least half the locations we chose, that was certainly the case.
Brilliant. Thank you very much, Mark. That was Professor Mark Beach from Bristol University.
Dave, thank you. Mike in Colchester got in touch and said if you were to use a mobile phone on an aeroplane, for example, what would happen if you were passing between the base stations at 500 miles an hour? Well, it wouldn't really matter from a radio point of view because radio is moving at the speed of light, which is considerably faster than 500 miles an hour. So relative to that speed of light, so much bigger, it wouldn't really matter. It's whether the network could actually keep up with the very rapid transition between the different cells. Now, with mobile communications playing an increasingly major part in our lives, many people are quite worried, quite justifiably, about the potential health impacts of this technology. And for this reason, a large study, it's called Cosmos, has been set up to track the ongoing health of 250,000 mobile phone users over a 30-year period. The leader of the study is Professor Paul Elliott. He's from Imperial College in London, and he's with us. Hello, Paul.
Hi, Chris.
Now, every good study has got to have a fantastic acronym to represent it, Cosmos being no exception. What does it stand for?
So it's a cohort study on mobile phones and health, and the key there is that the cohort means it's, as you say, a prospective study over many years, following the health of people and in relation to their mobile phone usage.
It sounds fairly trivial, but I'm sure it's not, to recruit a huge number of people and then try to get data from them. So how have you gone about this? Who are the study subjects and how are you following them?
So we identified people through mobile phone companies who sent out a large number of letters to subscribers, and the idea was to get people at different levels of usage, low, medium, high, so that we can get a broad range of use. So all these letters went out to subscribers in the UK, and then we invited people who received those letters to log into our website and answer questionnaire and give consent to take part in the study.
How often are you following the people up?
They give consent to us getting copies of their usage of mobile phones through the operators every year, so we get 3 months usage every year. And then the idea is to go back to them also on regular intervals with questionnaires, and regular being over a 4-year period. So we plan to go back to them with a questionnaire.
What about keeping in touch with them? Because one problem that big longitudinal studies like yours often face is people who get lost to follow-up for various reasons. So how are you going to make sure you keep people in the loop?
Clearly, working on mobile phones is good because, we can track their phones through either directly through the participant or through the mobile phone operators. But the participants give consent also for us to track their health through routine registries such as cancer registry and also the mortality register, hospital admission registers. So we can actually track people. We can track their health even if we can't find the people themselves.
It's quite neat that you can get access to how often they spend on the phone, which enables you to establish the dose that they're getting, because obviously when one is looking for causation, whether something is actually linked to something causally, there's got to be a dose-dependent relationship there, hasn't there? The more you use something, the more of an outcome we should see.
Exactly. The key is to get exposure variation, as you say, which, the proxy will be how often people use the phone. And by stratifying the cohort at outset into low, medium and high users, we've actually got a very good distribution at baseline on usage. And then we need to follow up through the continual looking at the mobile phone records, how much people are actually using. And then, as you say, one's looking for a dose effect in terms of potential health outcomes.
Now, one possible confounder here could be that not everyone uses their phone with it glued to their head. Some people use their phone with it on the table in front of them and they're watching some text coming up or Twitter feed and things like that. Can you discriminate between active calls where someone is dosing their brain with radiation at very close measures and a more distant operation like that?
Yes, we can differentiate between data use and SMS and active phone use. But of course, some people, even with active phone use, will use a hands-free device which will reduce the exposure to the head. So we do ask about use of hands-free devices as well.
What about kiddies, though? Because one thing I've heard people will say a lot is obviously as children are growing up, their bones are less dense, therefore their skull is less dense, therefore the attenuation of any microwaves coming out of the phone going into the brain will be lower in a child, so their relative dose to potentially sensitive tissue inside could be higher. Have you got them represented in your cohort too?
No, our study is a study of adults, but you raise an important question that clearly children are exposed, and as you said earlier in your programme, there are more from what you said. Children have more phones than they have books, so this is clearly an issue, and it is a question for active research in terms of does use in children affect, for example, their concentration, their sleep, and this is something that, for example, the WHO has called for research on because children are under-researched currently.
So, OK, it sounds like the study has been well put together and you're going to follow these people up and we're going to see if there are any health outcomes. What do we already know about the risks, though, and is there any preliminary data to suggest that there might be an effect? In other words, what do you think might come up? If there is an effect, what are you expecting to see?
OK, so there have been a number of so-called case control studies, which is a different design where you go to cases of disease, in particular people who looked at different forms of brain cancer, and then a set of control participants who don't have the disease and ask about their use of mobile phone going backwards. So this is based on subjective reporting. Those studies have actually been reassuring with regard to use up to about 10 years. of usage. So that's good news. But what we don't know is about much longer term use, and that's where the Cosmos study will be very important, because we'll be able to follow people up over many years and many years of usage.
Indeed, it takes 50, 60 years of dedicated subscription to cigarettes and a smoking habit to get lung cancer. So it may be that just looking in the near term, which many of these studies have, is just too short for us to see enough dose to see a small or marginal increase in, say, brain cancer rates, if there is a risk of that.
That's absolutely correct, yeah, I agree.
So where do you see this actually playing out to now? Are you going to stick with this cohort, or are you going to then build in additional secondary people who will come along behind this initial group in order to address some of the other questions that you've raised with us today?
So the cohort is a multinational study. So the UK is one component, and we have colleagues also working with us in various other countries, Denmark, Sweden, Finland and the Netherlands. The idea, as you say, is to get to a cohort of around 250,000 people. The study is open to other countries to take part as long as they can follow the protocol. And I think clearly the larger the study, the more power it will have to detect what might be quite small effects, if there is indeed any effect of long-term mobile phone use on health.
Paul, thank you very much. That's Paul Elliott from Imperial College in London. And this is The Naked Scientists with me, Chris Smith, and with Dave Ansell. We're discussing mobile phone technology and its possible health impacts this week with Paul Elliott. He's from Imperial College in London, and Mark Beach joins us from Bristol University. Both of you got a roundup of questions for you. On the health side, Paul, Lane, Seed Larson and also Egley in Facebook have commented on the health effects, saying, can mobile phones really lead to cancer? In other words, what might be the mechanism? And if not cancer, says Egley, what sorts of other diseases? Paul?
OK, so we don't have a biological mechanism to explain why mobile phones might cause cancer. So this is, if you like, the study is taking a long-term view because we don't have a mechanism. And as well as looking at cancers, we'll be looking at other neurological degenerative diseases such as motor neuron disease, Alzheimer's disease, Parkinson's disease, and cerebrovascular disease.
Thank you very much. This is one probably for you, Mark. Joshua Spell says, I've always wanted to know why I can be standing in the same spot, yet my reception can go from full bars to a low enough signal for a call to drop for no reason. And that's actually a point echoed by Francis, who's called in on the phone and says, the only place I can use my mobile phone is in the loft of my house and occasionally by the fridge. What can I do about this, Mark?
In terms of the signal dropping on the mobile phone from full bar to 0 bar, you've got to remember that things are moving in the environment around you. So it may have been a bus or a train that actually blocked the signal to your mobile phone from the cell site, and that's why the call dropped out. In terms of indoor coverage, yes, that can be very patchy. There can be metal objects around the house that actually block the signal, and usually gaining height by going upstairs is often the solution. Of course, we could turn around and raise the power of the base station sites, and there's certainly a reluctance for doing that, maybe on health grounds, and we haven't got any definitive evidence one way or the other there, but also just in terms of green issues associated with mobile phone technology. We're doing everything we can to make the system operate at very low power.
Thank you, Paul. This is a very important point, I think, for you, Paul. From Nelson Gachora, who's actually in Kenya, and he says mobile phone masts are springing up next to people's houses, and in some cases they're very, very close, 10 metres away from someone's home. Now, obviously, if people are in that situation but they haven't got a mobile phone, they're going to be outside the scope of a study like yours, aren't they? But how can you take into account those effects?
Yes, absolutely. People are not going to be in our study, but we have actually carried out a large national study in England and Wales looking at mobile phone mast emissions and proximity to masts and childhood cancers, and found no association whatsoever between the masts and the cancers. And of course the exposures that people receive from the masts are orders of magnitude lower than they get from putting a phone to their head.
Which is very reassuring. Thank you very much. Paul Elliott. I've got a question here from Ahensi Toto on Facebook, and he says, why is it that when you don't have a signal, you can nonetheless still communicate with emergency numbers? Why can't the cell phone just use whatever channel that is?
Okay, in a mobile phone network, we have what we call broadcast control channels and the traffic channels that are actual general communications go out on. The broadcast control channels can also carry the emergency calls and also your SMS messages. So yes, it does happen that sometimes you've only got emergency cover and not general call cover.
Terrific. Paul, this one's probably a good one for you because Mikey213 on Twitter said, should men keep mobiles in their pockets? In other words, is there a danger to their crown jewels? I guess this is important because obviously, is your study looking at anatomy as well? Because mobile phones spend quite a high proportion of their time in contact with certain bits of the body.
Yes, this isn't something that is easy to study. There isn't really any evidence to suggest that mobile phones have an effect on fertility, but it is an open question, and it's certainly something, for example, that the WHO, World Health Organization, are interested in. We don't really have a lot of data on that in our study because the exposure assessment is relying on the use of the phone and when it's being used rather than when it's sitting quiet. Of course, exposure is much less when you're not actually speaking. I mean, it's just handshaking to the mobile phone base station.
Mark, here's one for you. Louise Allen says, how does a text message get from one phone to another?
Okay, the characters that you type into the phone get sent as a data message back to the cell site, and attached to that is the mobile phone number of the person you wish to send it to. So that's routed through the network, and the message is dispatched to that phone.
Did I hear somewhere that the text message was just put into a bit of spare space, which they had on the way that they designed their system, almost put in as an afterthought very, very late on in the design?
Well, it wasn't actually put in as an afterthought. The original concept behind the short message service was to help the engineers who were effectively rolling out the network and putting the base stations up and adjusting all the parameters that make the network tick. So this is a way for them to report back how well it was working. And they suddenly repurposed that for the commercial service that we have today for texting.
Isn't it amazing how these things happen? This one, Paul, is interesting. Janet says, well, what actually constitutes heavy mobile phone use? Have you got any feel for what the dose is for someone who is a heavy user versus someone who's an incidental occasional user?
Well, we asked the mobile phone companies to stratify on their own data that they have, and of course this is commercial data. But we have published some data from our initial pilot studies that had a distribution of usage from very low, less than 5 minutes a week, to more than 6 hours a week. So we have a spread right across that range.
I think I probably fall somewhere in the middle of that. Hope I'm okay. Thank you very much, Paul. And probably one last one, Mark, this is definitely up your street, because Carl Keogh has got in touch. He's in Australia by email, and he says, do modern mobile phones put out weaker signals than earlier generations of phones did?
Yes, the transmit power of the mobile devices is actually dropping, although you may think your battery life is quite poor these days if you've got a smartphone. It's not to do with the RF energy coming off the phone, it's more to do with the display technology and the fancy things to do with the application. So transmit power is going down, and as I said earlier, we need to get it down in case there are any concerns on the health side, but also in terms of conserving energy and being more green.
So are they managing that by basically having better base stations or putting them close together?
The antenna technology has a big place to play in terms of reducing the transmit power. And there's also a big trend today to go for smaller cell sizes, and also the use of a thing called the femtocell, where effectively you've got a little mini base station inside your house. The range is very low, and phones power control themselves, so the transmit power will be exceptionally low.
That sounds good. Where can I get one of those? Thank you very much. Dave, one very quick one for you to do in 30 seconds, which comes from Anthony Lewis, and he says, why do speakers make the same odd noise when they are near a ringing phone and they intercept signal?
Okay, basically the phone is sending out a signal to all of the nearby base stations, essentially telling it where it is, and I think possibly also allowing the base station to characterise what direction it should send the signal in to get it, and all sorts of other things like that. And so it does it just before it picks up the signal and also does it randomly during the day, just so the base station knows where it is.
So you get an induced current in the speaker wire and off it goes. Thank you, Dave. Right, well, from one set of hard questions to another, it's time for our question of the week with Diana O'Carroll.
This week we're in some hot water.
Hi Diana, this is Francis Tapon and I have your question of the week. I'm in Croatia and I'm having a debate with my friend about water heaters. I have a water heater in my bathroom. I take 1 shower per day. I set it at just the right level so that it gives me just enough hot water for a 5-minute shower, no more. My friend says I'm being inefficient and I'm not saving enough energy. He says I should leave the boiler on 24 hours a day because it takes a minimal amount of energy to keep the water hot once it's hot. If I turn it off, the water cools and then must be reheated from scratch, requiring far more energy than if I had left it on all the time. Who's right?
Does it use less energy to keep hot water hot or heat it up from cold only when it's needed?
My name's Hugh Hunt from the Cambridge University Engineering Department. Well, this is a very interesting and topical question. If the hot water is stored in a perfectly insulated tank, then it makes no difference whether the water is heated 1 hour before it's needed, or 1 day before, or even 1 year before. There's nothing at all to be gained from heating the water up 22 hours in advance, but that requires that the insulation is perfect. In reality, insulation is not perfect, and the water heated in advance will lose some heat, and this heat cannot be recovered. It's the same as when we're boiling water for a cup of tea. If we boil the water when we need it, well, that makes sense because the kettle is not that well insulated. If we boiled the water an hour in advance, the water would be cold when we needed it. But how much energy wastage are we talking about? Well, suppose a 5-minute shower uses 60 litres of water, which is about right, and suppose the water is delivered at about 40 degrees, which is about right. And in the winter, the water is cold, somewhere around 0, which is sort of about right. So we're talking about 4 kilojoules per degree per litre of water. Now, suppose the tank loses maybe 10% of its heat in 24 hours. Well, then that's a loss of getting up to 1 megajoule of heat. That's equivalent to running an electric kettle for 6 minutes, enough to boil the water for several cups of tea. So if you're the kind of person who's bothered not to overfill the kettle when making a cup of tea, then you should certainly follow our Croatian friend's example and only heat the shower water when it's needed.
As no water heater is perfectly insulated for your shower water, it's most cost-effective to only heat the water you need. On the forum, Giza said that the most efficient water heaters probably aren't geared up to be the most efficient water storers. Percepts also said that insulation is the key, but that hot water showers were for wimps. Ron Neunerson on Facebook said that his sun collector keeps the hot water hot, which is even more efficient. But from bagging up the boiler to bags under the eyes now.
This is Eduardo from the beautiful Shenandoah Valley in the United States. And my question is, why does a lack of sleep cause dark circles under the eyes? I have dark circles under my eyes pretty much permanently, which people are always pointing out to me, as if I didn't know it.
Why do we get circles under the eyes? Answers to Chris at thenakedscientists.com. You can use the forum, which is at thenakedscientists.com/forum. You can Facebook us, or you can tweet at Naked Scientists.
Yes, do tell me. Do put me out of my misery. Thank you very much. Diana O'Carroll. And she'll be back next week with the answer. That's all we have time for this week. Thank you very much to our guests Paul Elliott and Mark Beach, and also to our production team, Mira Senthilingam, Diana O'Carroll, Ben Valsler and James Abbott. Next week, it's our Q&A special, so you can send in all of your science questions. We'll have a special focus on the radioactivity situation in Japan. Write to us, Chris at thenakedscientist.com, or you can tweet at Naked Scientists. Have a very nice evening, and see you next time.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.